Potential energy versus kinetic energy, exploring the basics of energy forms. Potential energy and kinetic energy are fundamental concepts in physics that describe different forms of energy associated with the position and motion of objects. Understanding their distinctions is essential in analyzing energy transformations and applications in various scientific and everyday contexts. 1. Potential energy overview. Potential energy is energy that is stored in an object due to its position or configuration relative to other objects, or due to internal stresses within the object. It represents the potential to do work or cause changes in a system if released or allowed to move. Potential energy is measured in joules, J, and exists in various forms such as gravitational potential energy and elastic potential energy. 2. Forms of potential energy. Gravitational potential energy is associated with an object's position relative to a gravitational field, such as a ball held above the ground. The higher the object is lifted, the greater its potential energy due to gravity. Elastic potential energy, on the other hand, is stored in objects that can be compressed or stretched, such as a spring or a stretched rubber band. 3. Calculation. The formula for gravitational potential energy is gravitational potential energy equals mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height or distance above a reference point. 4. Kinetic energy overview. Kinetic energy, on the other hand, is the energy an object possesses due to its motion. It depends on the object's mass and velocity and is also measured in joules, J. Kinetic energy increases with the square of the velocity, meaning doubling the velocity quadruples the kinetic energy. 6. Relationship. The key difference between potential energy and kinetic energy lies in their sources and manifestations. Potential energy is associated with an object's position or configuration, representing stored energy that can be released to do work. Kinetic energy, on the other hand, is associated with an object's motion, representing energy in motion that can perform work or cause changes in its surroundings. 7. Transformation. Energy can transform between potential and kinetic forms. For example, when a ball is dropped from a height, its gravitational potential energy decreases as it falls due to its changing height, while its kinetic energy increases due to its increasing velocity. At the bottom of its fall, the potential energy is minimal, close to zero, and the kinetic energy is maximal, maximum velocity. 8. Applications. Potential and kinetic energies are fundamental in understanding mechanical systems, energy transfers in physics, and practical applications such as designing roller coasters, calculating energy requirements in engineering, and optimizing energy efficiency in various technologies. Conclusion. Potential energy and kinetic energy are essential concepts in physics that describe energy forms associated with an object's position and motion, respectively. Potential energy represents stored energy due to position or configuration, while kinetic energy represents energy in motion. Understanding the differences between potential energy and kinetic energy helps in analyzing energy transformations, calculating energy transfers, and applying principles of conservation in scientific, engineering, and everyday contexts. Newton's first law versus Newton's second law of motion. Understanding fundamental principles. Newton's laws of motion are foundational principles in classical mechanics that describe the behavior of objects in response to forces and their interactions. Newton's first and second laws of motion outline fundamental concepts concerning inertia, force, and acceleration, providing insights into how objects move and interact in the physical world. 1. Newton's first law of motion, law of inertia. Newton's first law states that an object at rest will remain at rest, and an object in motion will continue moving at a constant velocity unless acted upon by an external force. This law introduces the concept of inertia, which is the tendency of objects to resist changes in their state of motion. 2. Inertia. Inertia is a property of matter where objects with more mass have greater inertia, making them more resistant to changes in motion. It explains why heavier objects require more force to accelerate or decelerate compared to lighter objects. 3. Practical example. For example, A book resting on a table remains stationary until a force, such as a push or pull, is applied to move it. Once in motion, the book continues moving at a constant speed in a straight line unless another force, like friction or gravity, acts upon it. 4. Newton's second law of motion. Newton's second law relates the net force acting on an object to its mass and acceleration. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. 5. Acceleration. According to Newton's second law, if the net force acting on an object is increased, its acceleration also increases, assuming mass remains constant. Conversely, if the mass of the object increases, more force is required to achieve the same acceleration. 6. Practical example. For instance, pushing a car requires more force to accelerate it compared to pushing a bicycle because the car has a greater mass. This illustrates how mass affects the amount of force needed to produce a given acceleration, as described by Newton's second law. 7. Relationship. Newton's first law describes the behavior of objects in the absence of external forces, emphasizing inertia and the tendency of objects to maintain their state of motion. In contrast, Newton's second law explains how forces cause changes in motion, quantifying the relationship between force, mass, and acceleration in dynamic systems. 8. Applications. Newton's laws of motion are fundamental in physics, engineering, and various scientific disciplines for analyzing and predicting the behavior of objects under the influence of forces. They provide a framework for understanding mechanical systems, designing technologies, and calculating the effects of forces on motion. Conclusion. Newton's first and second laws of motion are fundamental principles in classical mechanics that describe how objects move and interact under the influence of forces. Newton's first law introduces the concept of inertia, stating that objects at rest remain at rest and objects in motion continue moving unless acted upon by forces. Newton's second law relates the net force applied to an object to its mass and acceleration, quantifying how forces cause changes in motion. Understanding these laws is essential for analyzing motion, calculating forces, and applying principles of mechanics in scientific, engineering, and everyday contexts.